traffic.
Man, what you talking about, L.O.?
They don't understand what you're talking about. Enlighten, my brother.
Well, you can listen to me, but this is not a recital. I wanna rap to ya. I bought the title. If you live on the edge and you're struggling to survive, slow down, my people, cause you gotta stay alive. Alive and love, but we all should be. Don't you wanna live to be 103? In case you're wondering what I'm talking about drug abuse. Slow down. Drunk driving. Slow down. Child abuse. Slow down.
A subtlety in which it was natural for Cézanne to say, I see planes bestriding each other, and sometimes straight lines seem to me to fall. It is from the point of view of another subtlety that Clay could write. But he is one chosen that today comes near to the sacred places.
Same conditions. I shall illustrate on the sitar the nature of the variations and their relationship to the melody and the rhythm. The rag is kafi and the rhythm trital. This is an illustration only. Melody and variations are never played together in this manner. The variations are here superimposed on the melody. Incidentally, the odd bumping and squeaking noises you may hear occasionally on this record are made when I slide the brass frets up or down on the neck of the sitar in order to put them in proper positions for the different rags.
A pilot, to be skillful, must have more than an elementary knowledge of how to move the controls. He must have an adequate concept of the forces which act upon his plane, the way in which these forces may be advantageously used, and the limitations of his airplane. Now, to have complete mastery of his airplane, the pilot must understand why an airplane flies and how his application of the various controls affects its flight. Equipped with that understanding, he is able to fly within safe limits, to avoid dangerous practices, and to deal correctly with unexpected or unusual situations. Now, this recording, Theory of Flight, is a means by which you will be able to learn the truth behind powered flight. Enclosed with this album is a manual which is to be used as an integral part of this course. Do not listen to this record unless the book is in front of you. References will constantly be made to the numerous illustrations throughout the manual. the sound of a jet aircraft is heard. As we gaze skyward, we can't help but wonder what keeps those airplanes up there. Well, the reasons aren't very difficult to understand. Plate 1 shows the force that makes flight possible. That force is called lift. Lift is a force that is a result of atmospheric pressure acting upon the wings of an airplane. Before lift can be completely understood, a knowledge of the effects of an airflow is essential. Plate 2 shows a very special type of hollow tube. The ends of this chamber have larger openings compared to its narrow center section. This tube is called a Venturi tube. Plate 3 shows some air being blown through the left-hand opening of the chamber. As the air flows toward the center, it begins to travel through a smaller and smaller opening. Since large volumes of air are still entering the tube from the left, the air in the narrow center section is forced to speed up and make way. Whenever a stream of air travels through a narrow passageway, it is forced to pick up speed by the pressure of the large volume of air pushing onward toward the center of the tube. This fact is not only true of air, but also of water. Refer to Plate 4. It may have been a long time since you've gotten into a water fight with a garden hose. But remember when you were unable to reach your opponent because the hose wasn't long enough? Plate 5 shows a simple solution to this problem. All that was necessary was for you to put your thumb over the end of the hose. The water would then come out much faster and consequently would travel much farther. Result? Your opponent got wet. Plate 6 shows why. Without realizing it, you were creating your own Venturi tube. Just like air, the water was forced to speed up due to the pressure of the larger volume of water approaching the nozzle. Your thumb was the cause of the restriction, which is essentially the narrow portion of a Venturi tube. Now, we're going to leave the Venturi tube alone for the time being, but remember this principle. The velocity of air will always increase when traveling through relatively small openings. In the back of the Theory of Flight manual, there's a slip of paper. Take it out and hold it close to your mouth, as shown on Plate 7. Now, very slowly and easily, start to blow across the top of the paper. Blow a little harder, and just a little harder yet. The paper lifted, didn't it? As air flows over an object, a semi-vacuum or suction is created. The faster the airflow, the more the suction. This is what caused the paper to rise. Air flowing over the paper caused a vacuum, and the paper lifted. Atomizers and flit guns work on this very same principle. Plate 8 shows an atomizer close-up. The bulb is squeezed, and air is forced to pass over the opening of the tube that leads to the liquid in the container below. Since the air is flowing over the end of the tube, what do you suppose will happen? A suction or low-pressure area is formed, and the liquid is drawn up the tube and then is blown out the front. The liquid was drawn up the tube in the same manner that the paper was lifted when you blew across the top of it. Now let's summarize what we've learned so far. Plate 9. As air is forced into a restricted area, it increases in speed. Plate 10. When air flows over a surface, a vacuum or low-pressure area is formed. The faster the air flows, the greater will be the suction created. Just remember, air speed reduces pressure when flowing over an object. In just a few moments, we're going to apply these two principles to an airplane. But first, let's learn a little about the wing of an airplane. After all, this is what keeps the ship up. Plate 11 shows a cross-sectional view of a typical wing. The front edge of the wing is called the leading edge. The rear edge of the wing is called the trailing edge. An imaginary line connecting the leading edge and the trailing edge is called a chord. The curved surface forming the top of the wing is called the camber. A wing is said to have a large degree of camber when the top of the wing has a large curve. Plate 12 shows two wings. One has a high degree of camber, and the other has barely any camber at all. Become familiar with the various parts of a wing. We'll make reference to them. Plate 13 shows our typical wing in flight. The arrows represent air flowing over and under the wing. The straight lines above the wing represent an undisturbed, smooth flow of air. Take a careful look at the air flowing directly over the top of the wing. The air flowing over the top of the wing is traveling through a constricted area, bounded below by the camber of the wing and bounded above by the smooth layer of air. In other words, the air flowing directly above the wing is flowing through an area very similar to a venturi tube. And you know what happens in a venturi tube. The velocity of the air increases. Now you can see the purpose of having camber on a wing. The camber forms a semi-venturi tube. As the air speeds over the top of the wing, the results can be seen on plate 14. The increased airspeed over the wing creates a low-pressure area, and the wing is forced to lift. Blow across the piece of paper again. Watch it rise. The force causing the paper to lift and the force causing the wing to lift are one and the same. Air flowing over the curved surface increases in speed, and in doing so creates a vacuum, and the object rises. This is why an airplane is able to fly, any airplane, no matter how large or how small. The most important function of a wing is to create lift. Anything that's designed to create lift is called an airfoil. It should be obvious that a wing with a high degree of camber is capable of producing more lift than a wing with limited camber. A large camber will create a narrower venturi effect. Plate 15 shows the cross-sectional view of a high-lift wing and a low-lift wing. The high-lift wing is used on aircraft designed for carrying heavy loads. You can readily see that the bulky high-lift wing would have much more air resistance than the low-lift wing and would not be able to go as fast. Fighter and pursuit-type aircraft employ the thin, low-lift wing in order to attain the high speeds they do. In observing a few of today's modern aircraft, it is easy to spot a wing designed for high lift or a wing designed for high speed. The camber of the wing tells the whole story. On the majority of aircraft, however, a compromise between high lift and high speed is made, and a medium camber is used. Lift is one of the four major forces acting on an aircraft in flight. Another force is shown on plate 16. Now, as you may have already guessed, gravity, or just the weight of the airplane, is the second force. After all, if the ship had no weight, it wouldn't need lift. Plate 17 shows a third major force, thrust, or the forward motion of the aircraft. Thrust is provided by the propeller, or propellers on multi-engine aircraft. Plate 18 shows how the propeller pulls the airplane through the air. It pulls the airplane in the same manner that a boat would be pushed through water by its propeller. The power required to rotate the propeller is provided naturally by the engine. Although jet engines operate on a different principle than piston engines, the thrust produced is the same. It is still a propelling force. Both types of engines have one thing in common. Additional power must always be applied to gain additional thrust. Many people are under the impression that if you double the power of an airplane, you will double its speed. Well, this is not true. If it were, today's light aircraft would probably be cruising at speeds in excess of 500 miles per hour. Refer to plate 19, and we'll see why this is so. The main necessity for thrust is to counteract the fourth force acting upon an aircraft in flight, and that force is air resistance, or drag. Air resistance, or drag, tends to resist the movement of an object through the air. This is illustrated on plate 20. The faster we go, the more drag we encounter. If you're traveling 30 miles per hour in an automobile and put your hand out the window, you'll feel the air resisting your hand. Double the speed of the car to 60 miles per hour, and you'll notice the air pressure on your hand will quadruple. Now, if you do the same thing and double the speed of an airplane from 100 miles per hour to 200 miles per hour, the air resistance will again quadruple, as shown on plate 21. In other words, even though you only double the speed of an object, its drag will be increased fourfold. In order to counteract this added air resistance, the thrust or horsepower of the engine must not only be doubled, but actually must be more than quadrupled. As the drag increases, the power must be increased proportionately. Now, let's assume that you did install a very large engine in your plane so as to double its speed. The larger engine, along with the added fuel it requires, will, of course, burden the airplane with additional weight. If you increase the weight of an airplane, you will naturally need more lift. And the only way to increase the lift of an airplane is either to enlarge the wing or increase its camber. And this would create even more drag, and you'll need more power yet. Plate 22 shows the vicious cycle that plagues every airplane designer. You can't have everything in an airplane. You must sacrifice speed to get high lift, or vice versa. Well, you should now have a firm understanding of lift, drag, thrust, and gravity. These four forces act the same on a J-3 Cub as they do on a Boeing 707. You now know why an airplane flies. If you don't thoroughly understand this first lesson, do not proceed. Repeat the lesson over and over until you are sure you have learned it well. When you think you're ready, take the examination for Lesson 1 in the back of your manual. You are then ready for Lesson 2.
Here's a tune you should be tuning into. And if you don't, well then when it feels like it's the end, another love comes rushing.
A theory of waves. Having no surface of its own, the pond, under the shifting gray contingency of morning mists, extends even beyond the swamp beside it, until presently the thinning air declares itself to be no longer water, and the pond itself is still for a moment, and no longer air. Then waking bass glide from their sandy shelf, and sets of concentric circles everywhere expand through some imaginary thing whose existence must be assumed, until they meet, when incorporeal ripples, ring on ring, disturb a real surface, as if with dripping feet some dark hypothesis had made retreat. A theory of measure. We draw our own dimensions. After all the yardsticks are outlawed, still, in secrecy, our shadows at evening tell us that we're tall. We know that hours ripen, drop, and fall without a clock to pluck them hurriedly. We draw our own dimensions, after all, almost as frantically. It may appall us that we are much older when we see our shadows at evening. Tell us that we're tall, and we wonder what in us you think is small, remembering doodles that sometimes nervously we draw. Our own dimensions, after all, may be asserted somewhere in the scrawl. That we are shorter than our poplar tree, our shadows at evening tell us. That we're tall, the 15-year-old marks upon the wall, our shorter friends, both show us constantly. We draw our own dimensions. After all, our shadows at evening tell us that we're tall.
The time will come when we shall go traveling in space among the stars. When we do so, we shall see many strange things. We shall travel big distances. We shall meet objects which surpass our imagination. And we shall find out facts by direct experience about which we know at present only from theory, from the theory of relativity, which is due to Albert Einstein, whom I think some people call Einstein. I want to talk to you about this because the theory of relativity is to space travel what geography is to the exploration of the globe. Listen carefully, because Einstein's theory contradicts common sense. It will sound to you crazy. And if it does not sound to you crazy, that is a sure sign that you have not started to understand what we are talking about. What Einstein's theory says is that the world is a four-dimensional thing. It has 4 dimensions, 3 dimensions of space, and 1 dimension of time. Now you say, I have always known that. The essential part in Einstein's theory is that you cannot talk about space and time separately. You have to talk about them together, and when you do so, and when you look carefully, you see certain details which you have never dreamt of, and which in fact, as I said before, seem to contradict, actually do contradict common sense. But common sense is wrong, and Einstein is right. Let us start by thinking about something really simple, just 2 dimensions. Take a piece of paper and put 2 dots on it. Or take the top of the table and place your 2 index fingers on the top of the table. Now you can say the first dot is to the right of the second dot. Or, if you look at it from another direction, you may say no. The first dot is to the left of the second dot. And you are perfectly familiar with the idea that this all is in your point of view, that this is relative. It depends on the question whether you look at the two dots or at your two fingers from one side or from another side, from another direction. There is, however, something connected with the two dots which remains the same no matter how you look at it. This is their distance. You can easily calculate that distance if you know how far to the right the one dot is from the other and how far behind the one dot is from the other. How to make that calculation has been found out a few thousand years ago, first by the Babylonians and then later by Pythagoras. And it is well known as the theorem of Pythagoras. What you do is this. You take the distance between the 2 points, right and left. Let us say the first point is 5 inches to the right of the second. Then take the distance, how far the first point is behind the second. Let us say it is 10 inches behind the second. Then you will have to multiply 5 by 5, giving 25. You have to multiply 10 by 10, giving 100. And you have to add these two quantities, giving 125. And then you have to do something which is really very difficult to do. You have to find a number which, when multiplied by itself, will give 125. This is not quite easy. It can be done, and it is a number which is somewhere between 11 and 12. And that number is the distance between the 2 points, and it stays the same, no matter whether you look at your 2 points from one direction or from another. Well, there was a time, a few hundred years ago, when in the minds of most people the earth was flat. And for most of our movements, we could think of movements right and left, forward and backward. Of course, you could also move up and down, which was a third dimension. But up and down seemed a little bit different. It had some sort of an absolute meaning. And then came the discovery that the earth was round, and people in Australia were walking upside down when they were in Australia. This seemed absurd. By now, it no longer seems absurd. We got used to it. And we got used to it for a number of reasons. We got used to it because we have models. We can make globes, spheres, which we see even before we learn how to read and write, and get used to the idea that the earth is round. We furthermore get the idea that up and down is really not so different from right and left and backward and forward, and we can get that idea when we travel in an airplane and when the airplane banks. You look out at the window and the earth seems to be aslant, because for your feeling, whatever pulls you in a direction, whatever makes an object fall, determines the direction of down. For you, down seems to be different than simply the direction toward the earth. It is the direction toward the floor of the airplane, the direction in which the air pressure is supporting the plane, is supporting the wings of your plane. That for you locally seems down. And if you begin to get that feeling, it will be very easy to visualize, as we all know, that these three directions, forward and backward, right and left, up and down, are really three things which can be interchanged, but there is always one thing that remains the same, whether you just think of two directions or three, and that is the distance between 2 points, which you can calculate from the 3 numbers, the differences right and left, the difference back and forward, and the difference up and down. You multiply each of these numbers by itself, add the 3 numbers, and then try to find a number which, when multiplied by itself, gives the same result. And that is the distance. Now, just as we can move from 2 dimensions to 3, from a plane to the space, so in Einstein's thinking, we can move to the 4th dimension, and that will be what we call the world. A point in the world is determined by 4 statements: where it is in the right and left sense, where it is in the forward and backward sense, where it is in the up and down sense, and when did this particular thing happen. We talk about an event, a world event, which is determined by these 4 statements. Now, if you have a world event, then, or rather, if you have 2 world events, then there is something like a world distance between these 2 world events. And this world distance you can calculate by taking the 3 distances about which we talked before, multiply each of them by itself, and then take the time difference between the 2 events when they happened, multiply this time difference by the velocity of light, a very big number, and multiply the quantity which you get this way by itself. Now you have 3 quantities which you multiplied by themselves, and a 4th quantity which you have just calculated with the help of a time difference. And now you do something surprising. This last 4th quantity you subtract from the previous 3 quantities. And then you look for something which, when multiplied by itself, will give this number. And that is the world distance. Now, I am sure I have thoroughly confused you. But I will tell you why I talked about this distance and what follows from it. Because now comes the really great surprise. In Einstein's theory of relativity, the statement which is completely true, without any ambiguity whatsoever, and which yet is very, very hard to believe. Take 2 world events and imagine that they happen at the same time, but not at the same place. Then it is possible that you will find another observer who will say, no, these 2 events did not happen at the same time, but the one happened a little sooner and the other a little later. The question of earlier or later is dependent on the observer, just as the question right and left depends on the observer. But lest there be complete confusion, there is something which remains the same for all observers, and that is the distance between 2 world events. Now, if you have followed carefully, or even if you haven't, you will be able to see what use we can make of this strange world distance. There are certain kind of world distances which behave like 2 events, the one happening definitely sooner and the other happening definitely later. For instance, if I now say A and later say B, then there is no doubt that B has been said later than A. The same person has said it. It has been said, in fact, at the same place. And under those conditions, there is never any doubt that the one follows the other. The space distance is 0, and the first thing which we made out of time has been subtracted. So we have, as a result of our addition and subtraction, something that is strange. We had subtracted something from 0. We got something negative, and that is what is called a time-like distance. There is a time difference between two events, and no doubt about it. Also, if I am talking to you here and now, and then I have an appointment the day after tomorrow, let us say 100 miles from here, then also there is no doubt that this appointment will come later than my present talk. Because I actually can make it from here to there. And I can even imagine by saying, here is where I am. I can imagine that the two things, my talk now and my appointment a little later, have happened at the same place. However, I can imagine things happening quite differently. Let's think about an event here and now and something that happens half a second later in the moon. Is that second event in fact later? Well, light would take 1 second to get from here to the moon. And one consequence that Einstein's theory leads us to is this. Light is the fastest thing in the world. Nobody can catch up with it, and certainly nobody can travel faster than light. It might help you to remember this a little better if I tell you a limerick. It goes like this. There was once a lady called Bright who traveled much faster than light. She started one day on her relative way and came back on the previous night. What this limerick is telling you is, if you imagine that somebody can travel faster than light, then you put complete confusion into the ideas of sooner or later. If two events happen so close together in time that light cannot get from here to there in the time difference, then you might just as well think that the two events have happened simultaneously, and indeed there will be some observers to whom the two events will seem to differ only in the space and not in the time sequence of events. What the distance of two events is and what their time difference is will depend on the observer, just as the question of right and left and forward and backward depends on the observer. But there are some things which do not depend on the observer, and among others, these things are whether one can get from one event to the other, or whether two events are so close together in time that for some observers they may happen even at the same time. Now you may say, who cares of such very small time differences, like the time that is taken by the light to travel from here to there? Light can go around the Earth 7.5 times in 1 second. Surely such small time differences are of no interest, but they are. When you go traveling in space, then we are talking about distances which even light cannot cover, except in years or in centuries or in millions of years. And here I will tell you one very strange fact, and it is a fact. I have told you that from here to the next big assembly of stars, to the next spiral nebula, light takes 1 million years or a little more. Yet I will tell you that a space traveler can get there in his lifetime. And the reason is that what seems like 1 million years to one person does not necessarily seem like 1 million years to another one if he only travels fast enough. If a man would travel from here to Andromeda, for an observer on Earth, he will seem to take more than 1 million years. When he goes to Andromeda, returns and comes back, he will find that the Earth has gotten older by more than 2 million years. Yet, he might do it all in his own lifetime. This is how strange the theory is. Now, I hope that you carry away from this discussion the conviction: I do not understand this. I also hope that you will carry away the feeling there might be something behind it, and it's startling enough so that I will try to begin to square numbers and put them together and read up on it and begin to understand it. And I want to assure you of one thing. If you do so, you will find that the reason for the difficulty of the theory is not that it is complicated. It is that it contradicts your previous ideas. That is why you reject these ideas and why the ideas seem difficult to you. In actual fact, they are extremely simple. Let me tell you a little story. Albert Einstein, as you probably know, was not only a great physicist, he was also a violinist. And he used to play duets with the great pianist Schnabel. Well, even Einstein makes mistakes, particularly when it isn't in physics. And the story goes that Schnabel once took occasion to say, "Now look, Albert, this is simple. You just count. Can't you count? 1, 2, 3, 1, 2, 3. Just like that, can't you?" Well, there is one unfortunate thing about this story. It never happened. However, I would say that it is nevertheless true. And in repeating a true story, one should not be overly influenced by the accidents of the actual factual circumstances. The truth of the story is this, that Einstein liked simplicity, and he made a very simple theory. And the truth of the story is also this, that not to understand relativity, not to understand science, is something like not to understand music. And you begin to understand science or music when you begin to find out that you can love science or music, that you can begin to get really interested in ideas, in puzzles, in surprises. And then you will find that science is much more interesting than science fiction. And what is wrong with science fiction is that it is much too unimaginative.
Love
Once was the sign of courage. Now the world needs them to teach us a different stage.
Well, first, what is the theory? The theory is that in our dreams are composed, broadly speaking, of material drawn equally from our past and from our future. Dunn discovered that some of his dreams reflected the future. Not, and this is an important point, events that happened in the future, but his experience of them. Let me just make that point, that distinction clear. He dreams that there is a volcano eruption in an island which is under French dominion. There are gendarmes there and there are cafes, and that the number of killed are 10,000. 3 days later, he reads in the Daily Telegraph of the explosion of Montpellier in the island of Martinique. I think this was in the year 1905, and that the number killed was 10,000. 2 days later, a disclaimer is published in the Telegraph. There had been a misprint. It shouldn't have been 10,000, it should have been 1,000. Therefore, what Dunn dreamt about was not the future volcano eruption, but his experience of reading about it. Our dreams, therefore, reflect our future experience. What's the explanation? Well, Dunn has an extremely complicated theory of time, which it's awfully difficult to give in a word or two. But broadly speaking, the point is this. Think of time as something which is moving, flowing. Let's take the analogy of a moving staircase in a tube station. Now we've got to complicate it. The person who is experiencing is also in time. He has his own separate time. Think of him, therefore, as also traveling. He is walking up the staircase. But he's walking up the staircase backwards, so that his head is always turned down the stairs, and he can only see the steps he's come up. In other words, our normal consciousness only enables us to understand the past and the present. Now then, there are certain methods, certain techniques, by means of which the person on the staircase who's walking up it backwards can, as it were, be turned around so that he can look up the staircase instead of down. Then he'll be able to see the steps which are coming. Dunn's theory of that is connected with the unconscious. I can't describe this because it's complicated, but broadly speaking, it is by means of our unconscious self that we are enabled to turn around and look at the steps up the staircase along which we are traveling, as well as, or instead of, the steps below it. Actually, I ought to complicate it. He thinks that there are dozens and dozens of staircases, in fact an infinite number, but time, as he puts it, is serial. There are an infinite number of separate times, so what I really ought to say is an infinite number of separate staircases, and that by applying certain techniques you can move from one staircase to another. And when you're on the step of the second staircase, you can see some of the steps that are still to come on the first staircase.
Well, after just a few moments pause for a burst of applause all over the British Empire, I don't think anyone else feels very much inclined to do anything except say thank you for that.
Oh, that's the way they do it in the land of glitter and gold. Hey, when you're hot, and when you're not, you're not. All I'm trying to say, all that glitters ain't gold. No. Hey, when you're hot, and when you're not, you're not.
Heaving speech of air, a summer sound repeated in a summer without end and sound alone. But it was more than that, more even than her voice and ours. Among the meaningless plungings of water and the wind, theatrical distances, bronze shadows heaped on high blue contains the year and other years, and hymns and people without souvenir. The day enriches the year, not as embellishment. Stripped of remembrance, it displays its strength, the youth, the vital sun, the heroic power. In his own direction, how he had recomposed the pines, shifted the rocks, and picked his way among clouds, for the outlook that would be right, where he would be complete in an unexplained way from shore at night and disappeared. It is like a guitar left on a table by a woman who's forgotten it. It is like the feeling of a man who would have wept to step barefoot into reality, that would have wept and been happy, have shivered in the frost and cried out to feel it again, have run fingers over leaves and against the most coiled thorn, have seized on what was ugly and laughed as he sat there reading from out of the purple tabulae. That was not real at all. He wanted to feel the same way over and over. He wanted the river to go on flowing the same way, to keep on flowing. He wanted to walk beside it, under the buttonwoods, beneath the moon nailed fast. He wanted his heart to stop beating, his mind to rest. In a perfect beast, miraculous in its panache and swish. Birds twitter pandemonium around, the idea of the chevalier of chevaliers. The well over the water wallows of the vacant sea, declaiming with wide throat. Over all these, the mighty imagination triumphs like a trumpet and says, in this season of memory, when the leaves fall like things mournful of the past, keep quiet in the heart. In this illumined large, the veritable small, so that each of us beholds himself in you and hears his voice in yours, master and commiserable man, intent on your particles of never do, you're dozing in the depths of wakefulness, in the warmth of your only the wind seemed large and loud and high and strong. And as he thought, within the thought of the wind, not knowing that that thought was not his thought, nor anyone's, the appropriate image of himself so to transform itself, or else, and what meant more, to be transformed. He discovered the colors of the moon in a single spruce, when suddenly the tree stood dazzling in the air, and blue broke on him from the sun, a bullioned blue, a blue did he contain that had not yet been loosed, snarling in him for discovery as his attention spread, as if all his hereditary lights were suddenly increased by an access of color, a new and unobserved slight dithering, the smallest lamp which added its in the tumult of integrations out of the sky, and what we think, a breathing like the wind, a moving part of emotion, a discovery part of a discovery, a change part of a change, a sharing of color and being part of it. The afternoon.
The story is told that the Caliph Harun al-Rashid was one day seized by an unusual desire, that is unusual even for a caliph. He had the desire to get some scientific information. So he called in the wisest man available, and he was very wise indeed, of course. And the caliph asked him, I have heard that the earth is not quite flat, and I just cannot believe it. And the wise man said, Commander of the faithful, few men know it, but the earth is indeed not flat. The earth is the back of a giant turtle with sleepy eyes. And the caliph, whose scientific interest has been now thoroughly aroused, asked, But where is this turtle? Does he stand or does he swim? The wise man said, Commander of the faithful, this is a great secret, but the turtle swims in a big sea without a name. And the caliph thereupon asked the question, But where is that sea? And the wise man said, The answer to that question only I know in the whole world, and I found it out myself. This sea is in a big ball carried on the back of a white elephant with golden tusks. But, Commander of the faithful, on what the white elephant stands, nobody in the world knows. Well, our knowledge today about the world is a little bit different from the knowledge of that wise man. We know, of course, and you all know, that the world is not flat and that our earth is completely round. We know that it is sort of a big object, even though these days one can travel around it without too much difficulty. How big it is, I want to tell you, just for one reason, because I would like to help you get a measure of how big other things are. And in a strange way, this measure is obtained by thinking about a thing that travels very, very fast indeed. And that thing is light. Light travels so fast that if it could be made to travel on a curved path, it would travel around the Earth 7.5 times in 1 second. Now, this will help us to understand how big the rest of the universe is. The closest object outside the Earth, the object to which we shall first get when all of us space travelers really get going, is of course the moon. And that is approximately so far away that light takes 1 second to get from the moon to us, or of course from us to the moon. Nevertheless, when you travel to the moon yourself, you will have to take a little longer time than this 1 second, although it might not be, when we learn how to do it, much longer than the time will take to go from New York to Los Angeles. Then, beyond the moon, of course, the next really big object is the sun. That is far enough away so that light takes approximately 8 minutes to get from the sun to the earth. This is a distance which we call, therefore, 8 light minutes. Now, I cannot go on and talk about other things before I have told you a few things about the sun, some of which you may know already. One thing is that all the heat all the light, or most of it anyway, that we get here on Earth comes from the sun. But if we may follow the example of Harun al-Rashid and be a bit too inquisitive, we might ask, from where does the sun take its energy?